Hi friends, welcome back on our YouTube channel. In today's lecture of classical mechanics, we will discuss about central force and its characteristics. So, here we will discuss about central force and the characteristics of central force. So first of all, central force. Now what is central force? If the line of action of a force at different position of a particle always pass through a fixed point, as well as it is always directed towards or away from that point, and the magnitude of the force depends only on the distance of particle from the fixed point, not on the direction of line of action, then such type of force is known as central force. Electrostatic force, magnetostatic force, gravitational force, etc. are the examples of central force. If the fixed point is at origin, then the central force is given by F is equal to plus minus K function of R into R cap. This R cap is unit vector which is showing the direction, and f of R is any function of R or function of distance. Here K is constant. F of R is any function of the distance from origin, and R cap is our unit vector. In general, central force is given by F equal to K upon R raised to n plus minus R cap. This plus minus is due to force of attraction or repulsion. Now, if we take electrostatic force as central force, then electrostatic force is F equal to K Q1 Q2 upon R square into R cap. If we consider these two equations, then it is clear from this equation that this K is here replaced by K Q1 Q2. So, in electrostatic force, our capital K is actually K Q1 Q2. So K equal to K Q1 Q2, and K is actually 1 upon 4 pi epsilon naught. So capital K equal to Q1 Q2 upon 4 pi epsilon naught, and this epsilon naught is permittivity of free space, and its value is 8.85 into 10 raised to power minus 12 Coulomb square per Newton meter square. And F of R is here R raised to n, and in case of electrostatic force, R raised to n is R square. So F of R is 1 upon R square. Epsilon naught is permittivity of free space, and its value is 8.854 into 10 raised to power minus 12 Newton meter square per Coulomb square. If we consider magnetostatic force, then magnetostatic force is Fm equal to mu naught upon 4 pi m1 m2 upon R square R cap. So here capital K is mu naught upon 4 pi m1 m2, and mu naught is permeability of free space, and F of R is 1 upon R raised to n is actually, in case of magnetostatic force, is 1 upon R square. Here mu naught is permeability of free space, and its value is 4 pi into 10 raised to power minus 7 Weber per ampere meter. If we think about gravitational force, then Fg equal to G m1 m2 upon R square into minus R cap, and here capital K is G m1 m2, and this G is gravitational constant. So capital K equal to G m1 m2, and F of R equal to 1 upon R raised to n equal to 1 upon R square, and G is gravitational constant, and its value is 6.67 into 10 raised to power minus 11 Newton meter square per kilogram square. Now, characteristics of central force. So, first characteristic is angular momentum remains conserved. Second characteristic is a particle moving under the central force is always takes place in a plane. Next characteristic, when a particle moves under the central force, its total energy is conserved. Fourth one, central force is always a conservative force. And last one is speed of satellite at apogee and perigee. So these are the 5 characteristics which we describe here. Now, first one, angular momentum remains conserved. If m is mass of a particle, v is linear velocity of this particle, and p is linear momentum, and if L is angular momentum, then net torque acting on this particle will be tau equal to r cross f, and this r is actually position vector, and f is our central force, and central force is given by f of r into r cap. This f of r is any function of r, and r cap is our unit vector. Since r cap is a vector r upon magnitude r, so central force F equal to f of r into vector r upon magnitude r. Now, we substitute this value of capital F here. So, torque acting on particle tau equal to r cross f of r into vector r upon magnitude r. Since f of r and magnitude r are scalar quantity, so we take out from here. So f of r upon magnitude r into a vector r cross vector r. Since vector a cross a is 0, because a cross b is ab sin theta into n cap, and if we replace this b with a, then this will be a sin 0, because the angle between two same vector will be 0, because both vector will be parallel or overlap. So a cross a is always 0, so r cross r will be 0. So this will be 0, and therefore torque equal to 0. So there will be no torque on this particle if the particle is moving under the central force. Now, torque is 0 and r is position vector, p is linear momentum. So angular momentum L equal to r cross p. If we differentiate this with respect to time, then dl by dt equal to d by dt of r cross p. Now, we differentiate it by using u into v method. So first of all, r is constant and differential of p is dp by dt. And second time, p is constant and differential of r is dr by dt. So dl by dt equal to r cross dp by dt plus dr by dt cross p. Since from the Newton's second law, rate of change of linear momentum is always equal to the applied force, so dp by dt is actually f, and dr by dt is linear velocity. So we replace this dr by dt with v and this dp by dt with f. So dl by dt equal to r cross f plus v cross p, and p is our linear momentum, and linear momentum is mv. Now here m is scalar quantity, so this is actually m v cross v, and I already mentioned that the cross product of two same vector will be 0. So v cross v will be 0. It means v cross mv will be 0. So this is 0, and therefore dl by dt equal to r cross f, and r cross f is actually torque. So this is actually our torque. It means dl by dt equal to torque. So torque is actually the rate of change of angular momentum. It is same as the force in linear motion. So according to second law of Newton, in linear motion, rate of change of linear momentum is always equal to the applied force in the same way. If we take the Newton's second law in angular motion, then the rate of change of angular momentum will be equal to the applied torque. So tau equal to dl by dt. Now torque equal to 0, and we have proved that tau equal to dl by dt, it means dl by dt equals to 0. If a particle move under the influence of central force, then the rate of change of angular momentum is always 0, and rate of change of angular momentum is 0, it means L is a constant vector. Thus, the angular momentum remains conserved with respect to the central force. Now, next characteristic, a particle moving under the central force is always takes place in a plane. Since central force F of r equal to function of r into vector r upon magnitude r, and this F of r is actually the scalar function of distance. Since from the Newton's second law, torque equal to rate of change of angular momentum, so tau equal to dl by dt, and also torque equal to r cross f, and if we replace this f with this one, then tau equal to r cross f of r into vector r upon magnitude r. Now, f of r upon magnitude r is a scalar quantity, so we take out this one. So tau equal to f of r upon magnitude r into r cross r, and r cross r is 0, so torque is 0. Since the angular momentum of the particle about origin is L equal to r cross p, and torque equal to dl by dt, and since torque is 0, because the particle is moving under the central force, so dl by dt is 0, or L is constant vector. Now, L equals to r cross p, and L is a constant vector. So, if we operate this equation on either side with position vector r, so on taking the scalar product of this equation with r, so r dot L is equal to r dot r cross p. Since a dot b cross c equal to b dot c cross a equal to c dot a cross b, so this will be p dot r cross r, and r cross r is 0, so r dot L will be 0. So r dot L is 0, and if the scalar product of two vector quantities is 0, then both vector quantity will be perpendicular to each other. Therefore, the position vector r is always perpendicular to the constant vector L, because r dot L is 0, so r is perpendicular to L, or the position vector r is always perpendicular to the constant vector L. That is, the motion of a particle takes place in a plane for a central force. Now, next characteristic is, when a particle moves under the central force, its total energy is always conserved. For it, we consider a particle of mass m moving under the central force. Since the central force is conservative force, and central force F is equal to F of r into r cap, so F equal to minus del u by del r cap, and this u is actually potential energy, and the relation between potential energy and force is F equal to minus del u by del r cap. Here u is potential energy, and this F is actually F of r into r cap. So if we replace this with F of r into r cap, then r cap will be cancelled out. So F of r equal to minus del u by del r. Newton's second law of motion is F equal to ma, and a is the rate of change of velocity, and velocity is rate of change of position. So a can be replaced with d2r upon dt2. So F equal to m d2r upon dt2. Now, if we compare this equation and this equation, then m d2r upon dt2 is equal to minus del u by del r into r cap. So m d2r upon dt2 equal to minus del u by del r into r cap. Since the force is central or radial, therefore the radial acceleration in polar coordinate, and polar coordinate is actually r theta. So the radial acceleration in terms of r theta will be r double dot equal to r double dot minus r theta dot square into r cap. And theta dot is d theta by dt, and d theta by dt is angular velocity, which is represented by omega. So theta dot can be replaced with omega. So d2r upon dt2 is equal to d2r upon dt2 minus r omega square r cap. So here we replace this theta dot with omega, and this is actually d2r upon dt2, and in left hand side we have a vector quantity. So d2 vector r upon dt2. Now equation of motion will be m d2r upon dt2 minus r omega square r cap equal to minus del u by del r into r cap. So we just replace this d2r upon dt2 with this one, and we get this equation. Or m d2r upon dt2 minus m r omega square is equal to minus del u by del r. So here we cancel this r cap, and if we take m inside, so it is multiplied with this one and also with this one. Since the particle is moving under the central force, so its angular momentum will be conserved, which we prove in first characteristic. So L equal to r cross P, and P is mv, and L is constant, so L equal to r cross mv will be constant. In polar coordinate, velocity is given by vector v equal to r dot r cap plus r theta dot theta cap. Since L equal to m r cross v, so we transfer this m from here to here. So L equal to m r cross v, and v is this one. So we replace this v with this one. So L equal to m r cross dr by dt r cap plus r omega theta cap. So we replace this theta dot with omega and r dot with dr by dt. So L equal to m r cross dr by dt r cap cross r omega theta cap. R cap is actually a vector r upon magnitude r. Now this dr by dt is scalar quantity. So m dr by dt into r cross r, and this magnitude r is also a scalar quantity, so upon r, plus m r cross r omega theta cap, and r cross r is 0, so first vector will be 0. So here we have only m r cross r omega theta cap. So m by r dr by dt r cross r plus m r omega r cross theta cap. Now this is 0, so r cross r is 0. So L equal to m r omega into r cap cross theta cap, because this vector r is actually r into r cap, and r into r is r square. So m r square omega r cap cross theta cap. Since r cap is perpendicular to theta cap, so r cap cross theta cap will be z cap. So we replace this r cap cross theta cap with z cap. Z cap is also a unit vector which is perpendicular to the plane in which r cap and theta cap lies. So vector L equal to m r square omega z cap. Now we have already proved L equal to r cross mv is constant and L equal to m r square omega z cap. It means L equal to m r square omega z cap is a constant vector. If we take its magnitude, then L equal to mr square omega is constant. So vector L is a constant vector or mr square omega z cap is a constant vector, and if we take its magnitude, then L or mr square omega is a constant. So from here omega is L upon mr square, and m d2r upon dt2 minus mr omega square equal to minus del u by del r. So the equation of motion of the particle under the central force is m d2r upon dt2 minus mr, and this omega is replaced with this one. So L upon mr square whole square equal to minus del u by del r. Now if we open this whole square, then we have L square upon m square r raised to 4. We cancel one m and also one r. So this is actually minus L square upon mr cube. If we transfer this from here to here, then m d2r upon dt2 equal to L square upon mr cube minus del u by del r, or m d2r upon dt2 equal to minus d by dr of L square upon 2 mr square plus u, because if we open this one, then this will be minus L square upon 2m, and differential of 1 upon r square is minus 2 by r cube, and differential of u with respect to r with negative sign is minus du by dr. Now this 2 and 2 will be cancelled out, and this negative and negative will be cancelled out. So here we have L square upon m r cube, and this function minus du by dr is here. So we can easily write this relation in this way. Now we have derived this relation. Multiply this equation by dr by dt. So we multiplied this equation with dr by dt. So m d2r upon dt2 into dr by dt equal to minus d by dr of L square upon 2 mr square plus u dr by dt. Now here dr and dr will be cancelled out. So this is actually minus d by dt of L square upon 2 mr square plus u, and this is d by dt of half m dr by dt whole square. So if we differentiate this with respect to time, then we get easily this relation, because half m is constant and differential of dr by dt whole square is twice dr by dt, and again differential of dr by dt is d2r upon dt2. So this 2 and 2 will be cancelled out. So we get m dr by dt into d2r upon dt2, which is here. So we can write this relation in this way. We transfer this from here to here. So d by dt of half m dr by dt whole square plus L square upon 2 mr square plus u equal to 0. Since the differential of this quantity is 0, so this quantity will be constant. On integrating it, we get half m dr by dt whole square plus L square upon twice m r square plus u is constant, and this constant is represented here with E, and E is actually energy. So this is our total energy. Since L equal to m r square omega, so we replace this L with this one. So half m dr by dt whole square plus m square r raised to 4 omega square divided by twice m r square plus u equal to E. Now m and 1 m will be cancelled out, and r square will be cancelled out. So here we have half m dr by dt whole square plus half m r square omega square plus u equal to E, or half m dr by dt whole square plus r square omega square plus u equal to E. In polar coordinate, vector v is actually r dot r cap plus r theta dot theta cap, or v equal to dr by dt r cap plus r omega theta cap, because this theta dot is actually omega. Now v dot v is v square, so v dot v will be dr by dt whole square plus r square theta square, and v dot v is v square, so this is actually our v square. So half mv square plus u equal to E, and this is constant. So this is kinetic energy and this is potential energy. So total energy is always constant if a particle is moving under the central force. Therefore, the total energy for the motion under central force is always conserved. Now, central force is a conservative force. For a central force, F equal to F of r into r cap. F of r is a scalar function of distance. Now, if we take curl of this equation, so curl F equal to del cross F equal to del cross of F of r into r cap, and if we write it in terms of spherical polar coordinate, then this is 1 upon r square sin theta, r cap, r theta cap, r sin theta phi cap, del by del r, del by del theta, del by del phi, f of r 0, 0, because here we have f of r into r cap, so these two factor will be 0. Now, we open this one, so 1 upon r square sin theta as it is, r cap, del by del theta of 0 is 0, del by del phi of 0 is 0, so this is 0, plus r theta cap. Now, del by del phi of f of r minus del by del r of 0. So r theta cap del by del phi of f of r minus 0 plus r sin theta phi cap. So here, now del by del r of 0 is 0 minus del by del theta of f of r. So minus del by del theta of f of r, or this will be 1 upon r square sin theta, this is 0, so r theta cap del f of r upon del phi, so this one, minus r sin theta phi cap del f of r upon del theta, so minus r sin theta phi cap del f of r upon del theta, and f of r is a function of r, it does not depend on theta, so this is also 0 and this is also 0. Since f of r is the scalar function of distance r only, so del f of r upon del phi is 0 and del f of r upon del theta is 0. So this factor is 0, this factor is 0. So del cross f is 0. So del cross f is 0. Thus, the central force is always conservative force. A special case, f of r equal to minus k upon r raised to 1, f of r equal to minus k upon r square, f of r equal to minus k by r, f of r equal to minus kr. So these are the special case of central force. These all are the examples of central force and all are conservative force. Now, last characteristic is speed of satellite at apogee and perigee. Here, Sun and a planet is revolving around this Sun in elliptical orbit. So at some time it is at point P and in another time it is at point Q. So P is the point which is at the farthest position from Sun and Q is the point which is nearest to the Sun. Velocity of particle or velocity of planet when it is at point P is Vp and when it is at Q, Vq. So this is our maximum and this is our minimum. This is basically the consequence of constancy of angular momentum. So speed of satellite at apogee and perigee is actually the consequence of constancy of angular momentum. It means the angular momentum at every point will be constant. The maximum and minimum distant points on the elliptical path of the satellite are known as apogee and perigee respectively. Since P is the point which is at the maximum distance from Sun, so this is our apogee, and Q is the point which is at the minimum distance from Sun, so this is our perigee. Since the satellite moves under the effect of central force, therefore its angular momentum always remains constant. So mvpr maximum, which is the angular momentum at point P, equal to mvqr minimum, which is the angular momentum at Q. So angular momentum at P and angular momentum at Q will be same because the particle or satellite is moving under the effect of central force. Now m and m will be cancelled out. So Vp upon Vq equal to R minimum upon R maximum. So V is inversely proportional to R. It means the velocity of the particle will be maximum when R is minimum or the particle is very close to Sun, and the speed of satellite will be minimum when it is at the largest distance from the Sun or when it is at the farthest position from the Sun. So V is inversely proportional to R. Therefore, the ratio of the speed of the satellite at apogee and perigee is equal to the inverse ratio of their distance from the Sun. So here we end our session. In today's session we have discussed about central force and its characteristics. So goodbye.